Thank you so much, Duke. As Duke mentioned, I'm Yogashri Pradhan, and I work as a reservoir engineer at Endeavor Energy Resources. And I thought we'd start off the conversation. What better to start off the morning than talking about fracture-driven interactions? So I thought that for this product launch event, I wanted to bring everyone on the same page of some of the terms that we're going to start talking about. And I think the questions that you have, like the key development questions in development and in fracture-driven interactions, this tool can help you answer those questions and expedite some of those learnings that you may have that you've traditionally been using simulation for, like traditional simulation. I do want to start off before I talk in this presentation that since Omicron is still present and I know there's not as many people here, just still maintain your social distancing. And then another thing that I wanted to mention is that in your feedback, there's a form in your folder and there's a QR code in that form. Please be sure to provide as much feedback as possible for this kickoff event, because I know I've provided a lot of feedback to Duke regarding this tool. So for any feedback you have, please be sure to provide that, and that would be extremely useful because it just makes the tool stronger. Now I wanted to talk a little bit about fracture-driven interactions and bring everyone on the same page. I know in conversations that I've already had this morning, we've been talking about parent and child or primary and infill wells. In this presentation, I'm primarily going to talk about primary and infill wells. So a primary well is obviously the parent well, and then the infill well is the well that is produced right after the primary well. And then the conundrum that we have is if we don't use any mitigation efforts, the infill well creates asymmetric fractures, or there's asymmetric fractures that's towards the primary well. The other term that I want to mention is anytime I mention first order or second order or third order or primary wells, I'm referring to based on the position it is on next to the infill well or the primary well. So for instance, if it's a first order infill well, that means it's right next to the primary well. And every subsequent order or increasing order that you have for the infill well, that number increases and the farther away it is from the primary well. When I talk about fracture-driven interactions, in the paper 194349 from the Hydraulic Fracturing Technology Conference in 2019, where Endeavor presented a paper on a do-nothing case, we define FDIs as anything that's greater than 20 psi for what you call a frac hit. And then that can result in short-term and long-term connections. Anything that's less than 20 psi is classified as a frac shadow. Questions that you may have, especially we have a technical and a non-technical audience, so I thought this can be a question that's relatable to everybody in this space in reservoir engineering. But I wanted to whet the appetite of a couple questions that we have as a company and that you may also have as well, and you may also have other questions too, but I think the tool can answer. One question is, what is the resulting performance when the lower Sprayberry bench is completed after the Wolf Camp A and B? And sometimes you may not even want to have the primary infill well scenario because you know that either the primary well is going to take a hit and there's no guarantee for that primary well to come back online to pre-hit decline, or the infill well is going to take a hit because of asymmetrical fractures and there's a do-nothing case that's involved. So you may just have a co-developed case. But you also have the question is, what's the resulting performance of all the wells in a multiple stack co-developed scenario? And I think the tool can help you answer those questions by bypassing the traditional cycle time of simulation. So that's where SBF comes in. It's a software that implements physics-based methodology, and then it takes into account well spacing and timing, but there's also a data-driven approach by generating multiple type curves based on your geology and reservoir parameters, and you're essentially selecting the type curve based on your geology and reservoir parameters that you have. It's including I do mention, this slide mentions artificial lift, machine learning, and deep learning, but I really want everyone to focus on the deep learning aspect of it because that's what the tool is focused on. It's a subset of machine learning which contains brain-like logical structure of algorithms called artificial neural networks. This is just to bring everyone on the same page. It's a very simple slide, but I think what I'm trying to get at here is this tool is marrying the physics-based approaches with the data-driven approaches. Now, this is a workflow that we've primarily used within the company. This is a workflow that can help you figure out what exactly is the tool doing. You take your reservoir engineering parameters and your geology parameters, and you also have representative wells in the basin that you select. Then you generate probabilistic type curves. So now I'm going to the MVA development box. You generate probabilistic type curves in history matching using CMG. Then you input the generated type curves in a neural network. You train the deep learning model using a multi-regression algorithm. And then you create best fitting models, train the models, and test different sampling percentages. You select the best models and you upload it to the cloud. The history matching becomes really simple after that, because after when you input a range of geology reservoir parameters and generating a range of probabilistic type curves, you history match to determine relevant parameters for the neural network. So you're basically picking what type curve fits your geology and reservoir parameters. And after that, you can develop gun barrel views, assign the type curve that you created to those wells in the gun barrel views, and that's how you generate your EURs for oil, water, and gas, and then EURs of co-developed benches and different timings. So the results are pretty interesting to me, and as I mentioned before, it bypasses what you traditionally use in your cycle time for CMG. This is a case study that Dr. Lee already presented last year, but I want to revisit this because this is a common question that we have, especially when you develop multiple benches in the Permian or in unconventional plays. This particular case is in the Midland Basin. This is a common approach that we've used where you develop your Wolfcamp benches first, and then you come back and overfill your lower Sprayberry. And the question you have is, what's that percent EUR degradation if there is a percent EUR degradation with the lower Sprayberry in other Sprayberry benches? So these are the Sprayberry benches that are in question. You'll notice that because there are no frac barriers between the Wolfcamp and the Sprayberry benches, or not strong enough frac barriers between the Wolfcamp and Sprayberry benches, that's a subject of debate. You can space out your wells, and you can also figure out what's going to be the prediction of those spaced out Sprayberry benches. This is a slide showing what exactly is the percent degradation of your lower Sprayberry compared to the rest of your Sprayberry benches that you overfilled. And the physics makes sense. Your lower Sprayberry is going to take a hit compared to your other Sprayberry benches because of the proximity of the pressure depletion that the Wolfcamp benches created. And that's where I'm saying that the tool can help you answer those questions pretty quickly by using the data-driven approach with the physics-driven approach. You've already inputted your reservoir parameters, you've QC'd those reservoir parameters, you've generated the type curves needed, and then you pick the type curve that is representative to the gun barrel view that you create, and then you generate those predictions in the gun barrel view. I mentioned quite a bit in the workflow right now, but in the SBF workflow part of the presentation, you'll get more clarity. So SBF is a patented tool. It helps you answer some of the key questions. What is the most effective way to develop zones concurrently? The impact of approach on well interference, and then what is the optimal well spacing? Those are the encompassing questions that SBF is meant to answer by really quickly answering those questions by marrying the physics-driven and then the data-driven approach. So the next item on the agenda is the testimonials. And I wanted to kick off talking about the Midland Basin since we've had plenty of Delaware Basin case studies that Dr. Lee presented earlier today. For a show of hands, who works in the Permian? Like, who has assets that are based in the Permian? How about Midland? Okay, so I guess this is for this half of the room. But I wanted to go ahead and talk about, my presentation is going to be a little bit into the weeds of the deep learning, and then give you a couple more case studies in the Midland Basin, how we were able to understand overfill performance. As a company at Endeavor, we came up with this new vocabulary word that the infill for wells that are vertically adjacent to each other would be called overfills. So for example, you develop the Wolfcamp A and Wolfcamp B, and then a few years later you come over and then overfill with Lower Sprayberry. So anytime I mention overfill, I'm talking about infilling vertically adjacent to primarily the Wolfcamp A and Wolfcamp B benches. As I mentioned, this first half of the presentation, or most of my presentation, is going to get into the weeds of the deep learning. So for those of you who are machine learning AI enthusiasts, which I think most of you are in this room, I think this will be of interest for you. I'm going to start out with a few vocabulary words so we can orient ourselves in what exactly I'm going to be talking about. And one thing I do want to mention is that for those who have questions specific to deep learning, the developers in the back of the room will be more likely to answer those questions. And my perspective is coming from an end user input. I'm the one that's breaking the tool and telling SBF what exactly has been wrong with it so it can make the tool better. The first vocabulary word I want to start off is the node. It's called a neuron or perceptron. It's a computational unit that has one or more weighted input connections, a transfer function that combines the inputs in some way, and an output connection. Then the first other vocabulary word I want to mention is called the input layer. Let me see if I can get my... I have the laser pointer. So I'm talking about the right side of this chart where the input layer, it's the first layer in the neural network. It takes the input signals and passes them on to the next layer. The next one is called the hidden layers. So it has nodes and it applies different transformations to the input data. One hidden layer is a collection of neurons stacked vertically. So you have a number of hidden layers all the way from H1 to Hn. So you can have as many hidden layers as you want. And then you have the output layer, which is the last layer in the networks and receives input from the last hidden layer. With this layer, it can get the desired number of values in a desired range. So for the input layer, the data set is split into 3 sets. The well parameter columns are combined with 360 months, so it's the 30-year EUR of oil, gas, and water. And the data sets are also split into training and test sets, followed by an 80-20 rate. So 80% of the data is a training set, and then 20% is a test set. And then the data sets are shuffled each time as it goes through the hidden layers. So for those of you who are more into the deep learning, the activation of the input is called rectilinear unit or rectified linear unit. It's the most used activation function in deep learning models, and the function returns a 0 if it receives any negative input, but for any positive value, it returns the value back. So for the hidden layers, a neural network system is set with consistent number of n hidden layers, activation choices, and number of nodes. The algorithm generates a random number of hidden layers between each time a data set is shuffled. And then the activation choices for hidden layers are random in set. And then the number of nodes for hidden layers are also random. When I talked about the linear activation function, so it's a simple straight line activation function where the function is directly proportional to the weighted sum of neurons or input. The linear activation functions are better in giving a wide range of activations, and a line of positive slope may increase the firing rate as the input rate increases. So the activation functions, as this figure shows, it resides in the neurons. It's not necessarily in the input layer. So this is how the neural network exactly works. They're saved in the server. The API address of the server are saved in SBF, and the objects with all the required parameters will be sent to this address by SBF. So when Duke shows you the tool, or when we go through the demo version of the tool, you will see the input parameters, or exactly where you input your ranges of reservoir, geology, and PVT parameters into the tool. And then all those parameters will be sent to this address. The object that's computed in the server and the models, then in the server sends back the results to SBF. So once those parameters are sent, then the generated type well curves are then brought back to SBF, and that's where you get your ranges of type curves for you to start history matching. Again, in the demo, we'll show you what exactly the input ranges are, or what input types are for data types. But the one thing I want to show is you have a range of types you have a lot to input, which requires a lot of domain expertise. For instance, you have pressure drawdown per hour, initial flowing bottom hole pressure, your minimum flowing bottom hole pressure, your reservoir pressure, your bubble point pressure, your matrix permanent porosity that Dr. Lee showed for the history matching results for all 4 Delaware Basin case studies, your water saturation, and then you have your completion parameters such as your lateral length, hydraulic fracture saturation and permeability, cluster spacing, fracture hap length, and then one thing that we found as a company that we were able to calibrate our history matching with is use some of our frac models. And when you use your frac models, you're able to tell how much has been frac upward or frac downward. And you can use that as a guide to input in the ranges, how much have you fracked upward or how much have you fracked downward. For model parameters, you can also input what is the FDI factor for each well vertically and horizontally. So you can put how much FDI factor is on the top, on the bottom, to the left, or to the right. And in the deep learning tool, as Dr. Lee showed, you can tell how many wells is each well seeing to quantify what the degradation is going to be in a co-developed case and even in a primary infill well case. In the tool, you can also assign what the timing is. Dr. Lee showed in his presentation about the timing assignments for certain wells. It's a simple click on it's a simple assignment to represent what pressure depletion is for your primary wells. And then you have your bottom distance and average top distance. These are your spacing parameters that each well is seeing to quantify the spacing and the timing effects to influence the degradation. I showed this workflow before, but I think after enough case studies that we've seen earlier on the presentation, I wanted to revisit this, just so we can bake this in our brains. You use your geology, your PVT, and representative wells that you end up getting these parameters from. And then to develop the MVA, or to train the neural network, you generate probabilistic type well curves for history matching, and you run all of those curves into CMG. You train the deep learning model, and then you create best fitting models and select the best models and upload them to the cloud. For history matching and assumptions, you history match to determine relevant parameters for the neural network. And then when you develop those history match parameters, you assign each well in the gun barrel view those sets of parameters before you run the tool. And you use the algorithm to understand FDI impacts on different scenarios. So the outputs of what you already saw in the previous presentations are oil, gas, and water cumes. And you already saw what the user interface looks like in terms of the actual data versus the predicted data from SBF, as well as the associated EURs. Now this is a Midland Basin case study that I want to talk about. This is the AC fee from the Midland Basin, so this is based out of Midland County. You have your Wolfcamp B wells, and then you have your Wolfcamp A wells, and the objective was to look at what is the well performance for the Sprayberry wells after it has been overfilled after 4 years. So for the first couple of years, you had your Wolfcamp B and Wolfcamp A development, but you'll notice based on the shapes of the wells in this gun barrel view, how the timing is different. You assign history match parameters, like I mentioned, for the Wolfcamp A and Wolfcamp B, and you also assign history match parameters for the lower Sprayberry parameters, for example, to generate what would be the results for the blind test. So the average well performance that came out of these lower Sprayberry wells is around 560 MBO, or 498 MBO from the blind test. And then the average DCA, if using your standard reserves or using your standard procedure for reserves estimations, was around 560 MBO. So similar to some of the results that Dr. Lee presented in previous presentations, you're looking at an 11% difference. The last slide I want to show you is the Hutt-Donald. This is an objective to look at what is the Joe Mill and the lower this is the Joe Mill's performance, overfilling the Joe Mill after the lower Sprayberry Wolfcamp A and Wolfcamp B have been produced. And this is a case study after 3 years the well has been put under production. So there is 3 years worth of pressure depletion that is experienced by the Joe Mill. The actual DCA, or the blind test, was about 421 MBO on average for each of the Joe Mill wells, and the actual DCA for 4 of these wells is around 411. So you're looking at a 2.4% difference. The other thing to keep in mind is that when you're looking at these percent differences, there isn't a bias whether if the tool is either over-predicting or under-predicting consistently. That there is a randomness of residuals, or there's a randomness of percent error that is coming from the tool. The tool isn't consistently over-predicting or under-predicting, or it's not being completely optimistic or pessimistic. Those were the 2 cases that I want to show. I am open for questions, but I will save those questions after lunch, I believe. And now I am going to introduce our next speaker, which is Mr. Wade Warlow. Wade Warlow has been with Contango Oil and Gas since October 2019 as a senior reservoir engineering advisor and with 36 years of experience in the oil and gas industry. Before joining Contango, he was employed with White Star, Chaparral Energy, Chesapeake, Devon, and Marathon in various capacities. He has staff-level responsibilities in completions, production, reservoir, and business development as an acquisitions engineer. He's also served in various leadership roles as a reservoir engineering manager, division manager with leadership certifications from SMU and Cornell. He has graduated from the University of Oklahoma with a Bachelor of Science in Petroleum Engineering and a Master's in Business Administration Finance from Oklahoma City University. So please welcome Mr. Warlow.